Hi, my name is Jaebum Jung, and my title of topic is the problem solving in geometry. So I'm gonna just show some problem in geometry that are selected from some Wolfram community. And I'm gonna go over how to solve it using the Wolfram language geometry features. So what I'm gonna do is actually I'm gonna solve problems. So what kind of problem? I'm due to some time limit. I'm not gonna do like a Poincare conjecture theorem. Now it's theorem problem, but instead of that, I kind of select some problems over the Wolfram communities, and then I kind of ranked by the popularity and group them in certain area like here, construction, relation, measure, visualization. So if you see the question, some question quite simple, but it has some popularity. So that means in my point of view, some of the questions, for example, like, let me see, the first one. How do I draw triangle given the length of the side? Very basic geometry questions. And like before, like version 10, to solve this problem, we have to do some linear equation solving because we don't have functionality. So let's just check it. So for now, from version 10, I believe, we have new graphic primitive called triangle. So anyone know about this primitive? Heard of it? Probably some of them interested in graphic know about this, but not just triangle. We also have family of triangle like SSS triangle. It's something, some weird naming, but S means side. So this triangle construct actually input is the side length A, B, C. So exactly what this question about. So if you give length of side 3, 4, 5, for example, then return value will be the triangle. So this one now is point. And good thing about this function, not function, the constructor, certain cases you cannot construct triangle with any anonymous side. For example, this one, it tells you why you cannot build a triangle with this side length, like a 10 should be less than sum of sides 3 and 4. And other family, we have ASA, angle, side, angle, and also we have angle, angle, side, side, angle, side. So now this question, been a while, and there are many answers related to linear solve, reduce. Now you can just do with one command. And this is kind of similar problem, how to inscribe a circle in a given triangle. We have two new, not new, it's from version 10. We have primitive called inset sphere, circumsphere. Basically, input is point. This one can be extended to 3D and 4D. That's why 3D, so that's why we call it sphere. But if you give like 3 points, actually giving circle. So for example, I just make manipulator, changing the point into point, and then you see you have sphere inside, keep changing. And this is another function, comparison function, like it's giving the circle outside of given 3 points. And here's another basic question, how to construct simple polygon in a given point. Simple polygon means simply say the polygon without self-intersect. So when you have just 3 points, like triangle, you're never gonna have the self-intersect the triangle or polygon like this one. But this is one of the examples that which is not simple. So you see the self-intersection in the middle, right? So the question is, in such a case, how can we guarantee the return polygon is simple without this self-intersection? So one of the easiest way, you just plug in the point into convex hull mesh. This will create convex hull mesh. This is not, polygon right now, but you can extract the polygon. So now this is a simple polygon without the self-intersecting, and the given 4 point is this end vertices. But in some cases, if you have so many polygons like this, if you build convex hull mesh, you see some point inside of this mesh because this is convex. we don't allow this kind of concave, let's say down or whatever. In this case, if you just really want to put polygon that passing through all these points, given point, which is not convex, you can use find shortest draw. Now this question is turned out to be solve like a Chinese postman problem. So what this function does is find the path that touching every point without self-intersecting. So this is order of the given point. And if you use this order, you see now you have polygon which is satisfying our requirement. And it's about relation now. So what does it mean by relation? So relation between the object. So for example, like how to check if a 2D point is in polygon. So if you just imagine, it's very easy, right? You draw a polygon, see where the point is. If it's inside, then yes, it's inside. If it's outside, it's outside. But in realistic, I mean, if you want to program those things, it's not easy. Like back there, you have to consider, for example, like winding numbers and do some I mean, make like a series of linear equations and check it's inside, down, or up. It's not easy. So for like a new version 10 and 11, we kind of start to introduce some relation functions between regions. So like region nearest, region member, which is kind of main function, region disjoint within distance. And I will show you how we're going to use these functions to solve that simple problem. So here's the example. So I just pull out country data. So this is polygon of Australia. And I want to check some point is inside of this polygon or not. So here's the function region member. What it does is if you, the first argument will be just polygon also, any region, and then this point or one point, and it giving true or false. See, like this one is not in, this one is in, so false and true. Or the other way, if you use this polygon over and over again to check the membership, you can just create region member function, and this function can use repeatedly this point. So quite fast in this case. So here's some dynamic pane, locator pane example. So like red means it's inside, so it's quite fast. So you can dynamically see some point is inside or outside. And same question, now it's 3D point, but it doesn't make that much difference because region member, it doesn't matter the dimension, it just works. So for example, like here, so we have the graphics looks like a ball, and then the question is we want to verify this set of point is some point is inside, some point is outside. We just want to verify that. So first things, you discretize graphics and then check the region member. But in this case, you see there is nothing inside. What happened is this one actually looks like ball is sphere, so it doesn't have an inside. So it's empty object. So that means there is no term of inside and outside. It's only on the surface or not. So the easiest way to check that, if you see if it's solid, means it's filled in or not, you see it's false. So to solve this problem, we first need to make some solid object. So here, I just get the coordinate of this sphere and use the boundary as a boundary mesh region. So now we got the solid object, so we can now verify point inside. So here's the inside and outside. And you see this is point inside, and here's the outside. So, and combining, you can see the region member correctly specify outside and inside. And this another basic geometry question. So how to determine the center and radius of circle given some point in 3D. So we have given 6 points, and we want to see if this 6 point actually construct the circle in 3D space. And again, so what I'm gonna do is just using some simple geometry properties. So my plan is I construct two region. One is infinite plane that containing 3 points. 3 points, you got the plane, right? And then circumsphere, which is constructed by 3 points, the given 3 point, anything, and then one that is not in the plane. So you got the circumsphere, and if you see the intersection, because of the intersection between sphere and plane, definitely you will get the circle in the 3D. And here I just plotted given point. It looks like it is the case. And to verify it, I do region member, but here, surprisingly, we got some false case. This is due to some numerical, error, right? So given point was numeric. If you plug in the exact number, this will be true. But it's really thin line, and it's hard to really in or pull the numeric because of the digit and accuracy. Those things is not easy. But in this case, if you see the distance with the circle we create and the point, you see it's almost 0. So in this case, if you chop, you see this point indeed, at least it's almost control circle. And for computing the center, you're just using radius centroid with the circle we find, and radius will be just distance between the center we find at any point. So this is radius. And to verify this is actually the circle we want, I just using some formula for parametric circle in 3D and see it is the circle we want. So this is just, find duplicate in list of infinite line. So there are, to define infinite line, you can only use 2 points, but you can choose any 2 points. But it looks different, and we want to delete which one with the infinite line which on the same infinite line. Like here, we're using 4 infinite line, but if you graphic, we only see 2. So there are duplication. But if you're just using delete duplicate function, you cannot verify which one is the same. Because it delete duplicate, it just see the input form or full form in this case. But if you use region equal as a tester, then now it correctly delete the same region. So region equal is the actually see the geometry and check if it's same region or not. And now it's a measure. So it's for calculating volume or some curvature. Here's the example. So first one, calculate volume of convexor. It's just easy. We create convexor mesh. We can do region measure, which is kind of general function, but also we can just do volume. Nothing special. The good thing for region measure, at default, it checks the dimension of region, and using that as the deciding factor will be area or volume. But if you're just using volume, it always finds volume. What it means is for area, if you do this, then it's infinite because this is the solid object. So that's kind of different. And here's another similar problem, but now we want to find volume of Phobos, which is satellite of Mars. But if it's from example data, if you do volume, it gets 0. Why? We see so similar example in previously. It's not solid region Q. So I try to do same thing what I did, but it cannot construct boundary mesh region. That means there are some defect. So let's see what's going on here using the find mesh defect function. If you see it, it will show soon. You see there are overlapping faces that this one is the defect that prevent to construct boundary mesh region. Currently, we don't have, there are functions like a repair mesh, but this one, we don't support fixing overlapping faces. So I'm gonna do a little bit more work to do it. So I'm gonna just remove the overlapping faces from original mesh and then construct mesh. You see the little hole. This hole is created by removing that overlapping faces. And then I learn repair mesh. Now its problem is just filling the hole I created. And repair mesh can take care of it. So let me just show you. So you see, you don't see the hole anymore. And then now you can construct the boundary mesh region, which is solid object. And then you can compute volume. So using the Wolfram alpha, let's check what is actual volume of Phobos. So it's the 1,374 mile cube. And this one is actually kilometers. So let me convert to kilometer, then see. It's quite similar. You cannot see? Oh yeah, that's true. Good. Yeah. Now it's it, right? So now is computing the Gaussian curvature on discrete surface. So the formula I'm gonna use is this one. It's derived from Gauss-Bonnet theorem. So what this theorem says is the 2 pi minus sum of angle at each point and sum of area at each point divided by 3. So this is the simple formula you can find. So we have mesh. I just choose one ellipsoid, which is easy to verify the curvature computation is correct. So I gonna apply that formula that I show you. So first thing, for each point we need to find out the neighborhood polygon. This is undocumented, but you can use it on the mesh. You can find the connectivity matrix. 0,2 means point and then polygon. And what it does is, so for example, like here you see point index 1, you have 1, 2, 3, 4, 5, 6 polygon. This is polygon index. So this is how it looks like. This is point 1, and then you have 6 polygon around it. And using this polygon, this is function that I just defined to find angle. So here, this polygon angle will be angle between these two edges here. And just show you one case. This is angle at point P of each triangle you see here. And for area, you do the same thing, but now instead of computing angle, we use the area, which you can also find using property value. So this one return list of the area of each polygon in order. So area will be this. So I just gonna combine these two functions to define total the Gaussian curvature. So here this part connectivity matrix, and this is part for summing the area, and here summing angle, and then this is exactly what you see previous page, the formula for Gaussian curvature. And if I do this, so this is the set of Gaussian curvature for each point curvatures, and if I use this function that I define, so this is the graphic of Gaussian curvature on this cylinder. You see here curvature is a little bit higher because of the steep round. And here's some more example that I use that curvature function. So this left side, in this case, dodecahedron, which is defined by implicit equation, and then I define curvature using this original equation and formula. So this is kind of real curvature. And this is the one that estimated by the function I defined. So it's pretty good estimation in some sense. And here, this is mesh on example data, and this is curvature. And here's another example of curvature. It's Stefan Bonnie. And this is final the collection visualization. It's just visualization. The first one is about animating a Bolonoid diagram. What question was is like you have Bolonoid diagram of point, this random point, and can you animate some transformation from point to this Bolonoid diagram? So what it does here, so I just pick cells from this mesh region. So it's like here, cell, and this one is corresponding point in the cell. And then I apply some function, say Voronoi intersection. So region intersection between some circle, which will changing its size over time, and then the cell I extract here. So let me just show you instead of, okay, let me start from beginning. So this is original point with some little circle, and then if you're moving, it keep evolving and actually become to Voronoi mesh. So it's kind of transformation animation. And next one, the last one, is like a partition sphere. So this is the result what you want. So what was question is like we have given origin and radius, I mean just ball, and we have point and some face that dividing the sphere or ball. So, and then how can it partition those ball with the given section? I mean, so for example, like this one is just one face. So that face, I just define conical that passing through each face. So this you see here is the one partition, and other face also define another partition. So there's many ways, but like I said, it's just intuition. How can you get this partition? You can just intersect between this conical we just found and then ball, then we got the section. So that's what actually I did. So I just plug in this face given and create conical defined by those faces, and then just do the intersection. And I'm gonna get this partition here, like you see. And then mapping color to each side and combining results, then you got the partition of balls. So there's more questions, but you know, I only have like 20 minutes, so this is all I have for now. And then, you know, as you can see, some question is so trivial, but it's trivial, but hard to, you know, actually making function in like, for example, like well, polygon membership checking, those things. But those questions we keep checking here, listen the user's request, and then keep making some new function that make those job easy. So that's kind of thing what we are doing. And for the geometry, you know, the new framework allows to kind of intuitively solve certain problem like this one. This one is, you know, what only thing I did is just imagination, like an intersection of very straightforward, but it works. So those kind of things is one of the things we want. I mean, there will be more things you can do this way in upcoming version of Mathematica. So that's the end of talk, and here's, if anybody that doesn't check our geometry exhibition in the downstairs, is pretty cool. It's Unity integration with Mathematica, and we only have, it will close at 4, so you have 1.5 hours to check it if you don't. So, so yeah, that's it for today's talk. Yeah. And